So folks, here we have a double integral problem. Hopefully one of the things we took from this course is that before you tackle any double integral problem, you should think about the structure of both the integrand and the region that you're integrating over. And we can already see probably that polar coordinates might be the way to go with this. But let's go ahead and confirm that a little bit more so by looking at the region. So our region, the y coordinates are ranging from 0 to the square root of 9 minus x squared. That's the upper semicircle with a radius of 3. And the x coordinates are ranging between 0 and 3. So our region, R, is this region right here. And R is probably best described in terms of polar coordinates. So let's go ahead and do so. We could write R as the set of r comma theta such that 0 is less than or equal to r, which is less than or equal to 3, and 0 is less than or equal to theta, which is less than or equal to what? Pi over 2. So we're ready for a change of variables here, and we'll use the traditional one for polar coordinates where we say that x is equal to r times the cosine of theta, y is equal to r times the sine of theta. And then, of course, what we need to do is we need to say, well, how are we going to adjust the expression dy dx? And the answer is that that's going to be the Jacobian of r comma theta times dr d theta. Folks, you're welcome to, and I would not do this on an exam, remember that the Jacobian of r comma theta should just come out to be r. And you can go ahead and use that fact. For purposes of this review, I'd like to go ahead and remind you of how we get that Jacobian. So the Jacobian of r comma theta would be partial x, partial r, partial y, partial r, and then partial x, partial theta, partial y, partial theta. Let's go ahead and compute that. So if we take the partial derivative of this first function of x with respect to first r and then theta, what we have is the determinant of, so taking the partial with respect to r, we would just have the cosine of theta, and taking the partial derivative with respect to theta, we'd have minus r sine theta. Then let's take the expression for y, which we've written as r sine theta. If we take the partial derivative of y with respect to r, we just end up with the sine of theta. And if we take the partial derivative of y with respect to theta, we end up with r cosine theta. Computing this determinant gives us r cosine squared theta plus r sine squared theta, which simplifies to be just r, which is what we said it should be, and what you probably remember it to be, because the Jacobian for this particular transformation is not too difficult to recall. So let's go ahead and now set up our integral. The original integral could be thought of as the double integral over r of the square root of 9 minus x squared minus y squared dA, or you could go ahead and give it in terms of an iterated integral if you wish. But through our transformation into polar coordinates, we're going to rewrite this as the integral from 0 to pi over 2 times the integral from 0 to 3 of the square root of 9 minus r squared times r dr d theta, where, be a little bit careful here, this r came from the Jacobian that we computed before, and here I went ahead and made the substitution by thinking of this as minus x squared plus y squared, that would just be r squared through the usual formula. So let's go ahead and do this integral. So folks, what I did here in this part was I had to do some sort of u substitution, or at least compensate for that minus r squared term, the 9 minus r squared term sitting inside the square root. And then things cleaned up fairly nicely, and we were able to get our answer of 9 pi over 2. I hope this was helpful.